Hi guys, we have been discussing about the motion of charged particle in a magnetic field. So in my previous concept I discussed if a charged particle enters in a magnetic field perpendicular to the magnetic field, then the charged particle makes a circular motion, or other than that, if you take any angle, theta, some random angle, then it makes an helical path. So we need to notice two things when it comes to motion of a charged particle. When it comes to electric field, suppose a charge, positive charge moving in an electric field. Now in this case also there is a force, and that force is always acts downward direction on the charged particle because of the repulsive force, and the path of the charged particle in an electric field, especially for positive charge, it gives a parabolic path. But if we release the same charged particle in a magnetic field, and that motion gives a circular path. Yeah, here the magnetic field is only half portion, that's why here it made as semicircle. But if we take as full magnetic field, then it makes a circular path. And we know that the magnitude of the forces. So in an electric field, the magnitude of the force F equal to QE, the product of charge times electric field. This is the electric force, and magnetic force F equal to Q times V cross B, the velocity vector and the magnetic field vector. So if you combine these two, then that becomes Lorentz force. Now the motion of charged particle in a magnetic field, if it is a positively charged particle in electric field, the first case you take this is in electric field, it experiences a force. Yeah, charged particle in electric field experiences a force, and that force is in the direction of the field. So here I would like to highlight the force and electric field directions and comparison to that force and with the magnetic field direction. Here the charged particle is experiencing a force within the direction of the electric field. But when it comes to magnetic field, the charged particle will experience a force. That force is perpendicular to the magnetic field. Why this point is important at here? So when I need to calculate work done by the electric field or work done by charge, what the work formula can give? The product of force times displacement. In electric field there is a work because the force and displacement, they both are in the same direction. It goes to Fs cos theta, so theta value goes to 0. There is work which is done in the electric field. But in magnetic field, the force and displacement are perpendicular. So by the time the work is here equal to 0, because the cos 90 value goes to 0. So this is a very big important point when it comes to comparison of electric field and magnetic field, or to write the differences in the electric field and magnetic field. So the magnetic force is always perpendicular to the direction of the motion of the charged particle, that causes particle in circular motion. So that is one of the most important point. Other than that, while in an electric field can do work on particle, but magnetic field it cannot. because magnetic force never has a component that is parallel to particle motion. So that is the reason the particle speed remains constant. In circular motion, the particle speed remains constant. So try to get this point very carefully. Now today's concept, what happens if I make the charged particle move in combined electric field and magnetic field? This is a very important application which we need to do certain experiments. So the motion of charged particles combine electric field and magnetic field. Suppose for a moment we take electric field and magnetic field separately. So here a parallel plate capacitor like that. The red arrow mark shows the electric field direction and positive charge velocity direction is shown in purple. When it comes to magnetic field, the green arrow mark, the magnetic field is perpendicular to the electric field right at here. When the magnetic field is perpendicular to right electric field and charge motion is same. Now what happens if I combine these two? If we combine these two, electric field and magnetic field, if you place electric field exactly perpendicular to the magnetic field, so that is something like this. So let me see how this electric field is perpendicular to the magnetic field. It means we need to place such a way like that these two fields are crossed. So when electric field is perpendicular to the magnetic field, mind the arrow marks. Now the electric field and magnetic field are perpendicular and the direction of the charge, here the direction of charge is represented with as a purple arrow, and that direction of charge is perpendicular to the both. Now here the three, the electric field and magnetic field and the velocity of the particle. So these three are mutually perpendicular. So when this situation comes, when a charge kept in crossed electric field and magnetic fields, then this is an advantage. The motion of charged particles such as electrons can be controlled by combined electric field and magnetic field. So this is such a situations when it comes to us, when a charged particles are placed in crossed electric field and magnetic fields, especially when it comes to certain experiments, we need electrons, they move with a certain velocity. Now the motion of the charged particles can easily controlled by the crossed electric field and magnetic field. How it can be done? And before that, keep in mind that the electric force will be acts on electron, which is I am showing right at here. If you can describe the diagram. So here a crossed electric field and magnetic field right at now we will observe. So here the parallel plate capacitor will serve us as an electric field, and the cross marks are indication of the magnetic field. So in that both electric field and magnetic field both are perpendicular, they are crossed, and if you release an electron in this crossed electric field and magnetic field, so what happens? The electrons will experience force because of the both electric field and magnetic field, and right at here the both fields are perpendicular, and we need to keep in mind the force on electron is which acts upward direction, because the positive plate is in the upward direction. If you can notice it here, The positive plate is at here, so the electron will experience an upward force, and the magnetic force which acts on electron in this case, which is the downward direction. Now these two forces are acting at the same time on an electron which is moving through it. Now suppose if these two forces are equal, the force which acts on electrons due to electric field and the force which acts on electron due to magnetic field, if these two forces are equal, will the electron change its direction, means change its deflection? And we learned electrons will deflect in electric field just like parabolic path. In magnetic field it moves in a circular path. And if these two fields are acts on electrons at the same time, and if these two forces are equal, means if the forces are balanced, then the electrons it do not deflect, it takes a straight path. It means the effect of these two forces that gets nullified, it gets equal. Now that is the very advantage situations for us. Now that we call a device name known as velocity selector. Velocity selector is a device, just like a machine, just like a device, in that crossed electric field and magnetic fields are established. Through them, if you release an electron with this so many velocities, but in that velocities, if you need desire only one particular type of velocity for your experiment, now that velocity of electrons can controlled. That velocity of electrons can controlled by the applied electric field and magnetic field. How it can be controlled? Because if you just control the magnetic field applied equal to electric field, for the desired needed velocity of that particular electron or particular ion, then that velocity of that particular ion is used in your experiment. So this device name is known as velocity selector. So it is a device which uses a crossed electric fields and magnetic fields, select only those velocities for which the force of the magnetic field equal to the force on the electric field. Suppose if we can use positive ions, just we need to mind its directions, because magnetic field, electric field and force all are direction sensitives. And magnetic field having the cross product also, that is V bar cross B bar. So finally we can say about the velocity selector. Suppose here a source is a positive charge. Right now I am taking a positive charge source rather than an electron. So you can change the directions here itself. So the positive source charge is deflecting in a crossed electric field and magnetic field. If in case the force due to magnetic field equal to the force due to electric field. Now we know the two force formulas. Force due to magnetic field equal to BQV and force due to electric field equal to QV, and we can get the velocity equal to the ratios of electric field to magnetic field. So which is known as condition of velocities which comes out of that particular ion. So these crossed electric field, they are very useful to select desired velocity which we need for our experiment. So this is one of the feature which is used by J.J. Thomson in 1897 to measure charge to mass ratio of an electron. To measure charge to mass ratio, then only he said that the charge of electron and electron having the mass, by measuring its charge to mass ratio, that is also known as E by M ratio, charge to mass ratio of electron. So by the time J.J. Thomson he did a very good experiment, and that experiment is a very tedious experiment. So he used a cross electric field, and he used a small hole. In that he released electrons, and he started to count how many electrons are reaching down. So in that particular case he used this is a technique as velocity selector, how he can control the motion of the electrons. Once you can get the about that Thomson experiment, go through about that one. How he controlled the velocity of the electrons? So because by using the crossed electric field and magnetic field. So this is a simple expression, the velocity of electron V equal to E upon V.